All right. So in the previous lecture, we discussed about natural policy gradients and TRPO and PP. The whole topic of the lecture was about the step size, how much we can step along the gradient direction or along the natural policy direction that we came up with. Today's lecture is different. We'll see what can we do to learn deterministic policies. So there are two chunks of this lecture. The first is about deterministic policies and how do we take gradients in that case. And the second is about really stochastic policies, where we're going to change the reinforcement learning objective to promote stochasticity, okay? To reword a policy from being stochastic, okay? All right, so just to remind you, this is the standard policy reinforcement learning objective that we have put down. And this is the corresponding policy gradient that we came up with 2 lectures ago. We said we'll be computing the advantages of states and actions that show up in our trajectories by training a critic network, the value function, if you remember, and then using it to compute those advantages. And the question that I have today is the following. Imagine that instead of trying to maximizing rewards or returns of trajectories, we try to maximize the Q functions, like that. The Qs of the different states and actions. Now the Q function, we know the Q function, that's a big difference, right? So the reward function we do not know, but the Q we estimated. It's not the correct Q, but it is, we have an estimate of it. The question is, for you, can we backpropagate through that Q function approximator? And the answer is yes, we can, because it is differentiable. And the interesting thing is that if the policy is deterministic, we already know how to do that using the chain rule. So dq d theta, where theta are the parameters of our policy network, is exactly equal to q dq dA, dA d theta. So this is the chain rule. So my question for you is, why didn't we use, can we use that chain rule? Do we know how to use that chain rule when our policy is not deterministic, but rather is, for example, Gaussian, where we sample from it? Okay, so just to give you the big picture, we have put some objective down. Our goal is to estimate parameters for our policy network. These parameters, we call them theta, okay? And now, last time, we said that we don't know the reward function, right? And the way to do it, to essentially maximize this, expected returns, is through this likelihood ratio gradient estimator. Estimate some advantages and take the log grad p theta, if you remember, okay? Grad log p theta. Now the question is, if I use the Q function instead, the Q function is differentiable. I can differentiate it with respect to alpha, for example. Imagine you have the Q, the input is a state vector and an action vector, and the output is a scalar value, and your goal is to maximize the Q values with respect to the input alpha. Yes, you can totally do that in the differential function, all right? Now, if your policy is deterministic, then you can directly apply the chain rule. All right, so the gradient through the input action parameters can be propagated all the way to the parameters theta of the network that takes the state and spits out that action vector. All right, so let me show you the picture, okay? So and then don't worry, things are going to fall in place throughout the lecture. So here I have the states that, let's say, our agent visits. And for every state, our policy spits out an action. And the notation here is that for every deterministic variable, I have a square. And for every stochastic variable, I have a circle. Okay? And the reasons on states are stochastic variables is because the environment is stochastic. In this case, we will focus on deterministic policies. That's why you see that the alphas are inside squares. And you see that the theta parameters affect all those actions because you sample from your policy, you essentially compute those actions from the policy network that takes the state as input and spits out the action. And now we want to compute the expectation of the gradient of the Q with respect to the parameters theta. And this is exactly using the chain rule dq d alpha d theta. And this actually can be computed. And this was introduced in this paper of 2016, which is called continuous control with deep reinforcement learning. And this proposed that they're called deep deterministic policy gradients, or DDPG. So whenever you see in papers DDPG, this is precisely the algorithm that we'll discuss. And the big assumption here is your policy is deterministic, which means what? That the policy network does not parameterize a distribution from which the actions are sampled, like we had in the last two lectures, if you remember, with the softmax layer and the Gaussian layer. Now there is none of that. Directly, the policy network spits the vector for the action, which means what is the steering angle, how fast should I, press the gas, and so on. Whatever parameters you have in your action vector, like how should my robot gripper be arranged, etc. These are coming directly as scalar coordinates from our policy network. And visually, to see how the computational graph looks like, is like this. So we have a state that enters into that policy network, which spits out directly an action parameterization, which enters into that Q along with the state and spits out the Q of that state and action. Okay? And DDPG essentially says that in this special case of deterministic policies, you can backpropagate all the way from maximizing the Q values to updating the policy parameters theta mu. Okay? So again, what you see in the slide, we have a critic, theta Q, which given a state and action tells you how good is the state and action, and an actor, theta mu, that takes a space, spits out actions. And DDPG essentially tells you how to update the actor by backpropagating directly through the critic. And my question for you is the following. Did we use the critic's gradient? I mean, the critic in our previous, if you remember what we had concluded, although we said there are many actor-critic versions, we all had concluded that a critic would be a V, like the state value network, if you remember. But we also said that, instead of V, you can just dump the Qs there and do grad log p theta Q. That's fine. You can do that. My question for you is, in our policy gradient lectures, did we ever use the gradient of that Q network to update our policy parameters? Yes.
I don't think so. We use the value estimate of the critic as a baseline, but not the gradient.
Exactly. We use the critic as a baseline and also as a way to compute those advantages. You remember it's centenary world plus gamma, v of the next state minus v of the present state to make these alpha estimates. And that's it. No backpropagation. All right. Now we say you can backprop from Q for the special case where the policy is deterministic. All right. And now I'll show you the pseudocode. But do you see how, I mean, it's natural to be able, in that special case, you can apply the chain rule. All right. And of course, you don't have the perfect Q estimate. So again, we're going to iterate, which means I will collect trajectories. I'll compute the Q values, okay, which is the policy evaluation step. I'll backpropagate through the Q to update my policy, which is the policy improvement step. Now I'll recollect trajectories, recompute the Q, backpropagate, update the actor, and so on and so forth. Is that clear? Okay. Now my question for you is how we're going to compute the theta Qs. Does anybody have any idea there? Other person? So here so DDPG will show you a different way of updating the actor. Let me ask from a simple question. In policy gradients, how did we compute the critic? Does anybody remember? Yes.
The regression to compute the return.
Just a regression. So we train it to just being a standard regressor. That's what your colleague is saying. And do you remember what did we regress towards? What were the targets for every state? Yes?
We regress towards the Monte Carlo return or the 2D target.
Exactly. Guys, you really need to put everything together in your head. Estimating the Q's or the V's is just a regression, okay? Reward plus gamma, V of the next state, okay, that's all. And then this is your TD target, or sum of rewards from that state onwards till the end of the trajectory, and this is your MC target, and you just train a network to imitate those targets. That's it, all right? So this part is not going to change here. In DDPG, again, to compute the Q is just a standard regression problem. All right, let's look at it. Where it says fitting the Q function. And here the Q function is actually instantaneous reward plus gamma Q, the S of the next state, and the action that your network will take in the next state. All right, that sounds reasonable. Okay. Yeah, so this is the target. And and yes, that's how we're going to update the theta Qs of the critic. And the only thing that changes in DDPG is how you update the actor. All right. And here you don't see any grad log P theta anymore. What you see is the chain rule. Here is the chain rule. Grad of Q with respect to alpha, grad of mu, which is the alpha, with respect to theta mu. All right, this is the chain rule. All right. Now, the other thing that you need to be remembering is because we're training for a deterministic policy, to be able to collect trajectories, you cannot just deploy your policy because your policy is deterministic. You really need to add some noise, all right, to be able to explore. And this is what happens there in the green part. It says select an action by adding some Gaussian noise on the actions that your actor is spitting out. Is that clear? Does anybody want to remind us how we were exploring when we had policy gradient methods? Which also you will need to implement on homework too. Yes?
Our policy gives us a distribution and we sample from that distribution.
Exactly. Precisely that. There's no epsilon greedy because our policies were stochastic. And you know, there is this hack when you take also the gradient with respect to the entropy of your policy, which is very simple. You just differentiate the entropy, the formula of the entropy, and this essentially helps you, this distribution over actions at every state not to collapse, to be able to be fat enough so that you can keep exploring. All right? Yes.
I just an included kind of question. It looks like for the Q part, it's doing something like DQN.
Mm-hmm.
Is it different from, I mean, in DQN, the state, the action is in the trajectory, but it's being sampled on the previous network. But for that part, it looks like DQN.
This is precisely the DQN equivalent for continuous actions. That's absolutely right. And you know, in DQN, because you have discrete actions, you can do argmaxes. When you have continuous, you take gradient and try to maximize with respect to alpha. But actually, in the next slide, we say exactly this, I think. Yeah. This is precisely the equivalent, all right? But we have continuous actions here. There's no discrete actions in DDPG. It's for continuous control, right? That's exactly the title of the paper. Yes, so it's exactly what your colleague said. In the deep Q learning target is exactly immediate reward plus gamma, argmax across all alphas of the Q, right? And here we don't do argmax across all alphas. You actually put directly your policy, but your policy, the way it's computed is by taking the gradient through the Q with respect to alpha, right? So it's trying to do an argmax essentially. Okay, that's exactly right. And you see here we also have a two network for stability purposes, much like we had with the DQN. You remember, like we had one network to give us the targets, and this was kept frozen. And then every 1,000 steps, we would copy paste the weights, because if you only have one network, you have instability. All right, it's as if you're chasing your tail. So the same thing happens here. Exactly the same thing happens here. Yes?
Stability for the actors. It seems like we have both the networks have targets and.
Yes. So here, if you see the primes, right? These are the primes. These are the target networks. The target networks are only used to give you the targets for your queue. Exactly like in DQN, we use them to get the targets for our queue values. Yeah, exactly. So the actor parameters are part of that queue. Okay. Exactly. Any questions here, guys? Okay. So, I mean, I thought this interesting. So this method was used in many papers as a good baseline, etc. It does have high sensitivity in the hyperparameters, but the reason we present it is because we want you to put, side by side all the ways that we can take essentially derivatives, and why we use this specific way in this case and this other way in this specific case of deterministic policies, right, where you really can apply the chain rule. Yeah, so basically mainly for comparison purposes. Okay, so now here is my next question. Here's my next question. What happens? So far is very simple. We just said you have deterministic policy, you're going to do the chain rule. Now, what we're going to see is that even when your policy is Gaussian, you can still apply the chain rule. All right? Which I don't know if what we're going to see is the reparametrization trick of the Gaussian distribution. This reparametrization trick is going to show up in multiple cases in the course, but also in other courses. Some of you may have seen it before, but may not know now how to connect it. Now we're going to connect the reparametrization trick with this way of taking derivatives. Before we jump to that topic, do you have any questions? Okay. So here is, let's consider a very, very simple graph. We have a particular state, and here is the parameters theta of our actor, and this p theta of spits out actions, okay? And these actions, as you see, they're circles, so they're stochastic actions. You'll be sampling from that policy, and that action and the state enters to that reward function. Let's assume we know that reward function, and it spits out a reward, okay? And here is how this tiny little diagram adapts for our deterministic policy. Well, alpha is this function of the parameters theta, and the alphas are, squares because they're deterministic. And you know what? In that special case, if I want to maximize the reward function, which, as you might know, is an analytical function, I can just compute the gradient and apply the chain rule. D rho d alpha d theta. Is this natural for you guys? Do you feel natural? Exactly. So what we did 3 slides ago is, instead of rho, reward function, we don't know the reward function, we said we know the Q function. We're actually estimating it. So let's just take the derivative through the Q. That's all we did. All right? And by the way, DDPG is insanely simple to implement. We even had it in homeworks in previous semesters, but because now we added more homeworks on model-based RL, so don't think that is something exotic. You should feel comfortable if some people, we may ask you, for example, in a quiz to fill in, let's say, some pseudocode, right? So you should feel comfortable to do that. Yeah. Okay, great. So this is the chain rule. I don't see anything crazy here. Now here's what we're going to do. Let's go back and say that our policy is stochastic. Here is again the circle. And now I want again to learn theta in order to maximize the reward. Can somebody tell me how we're going to do that? What have we learned already? What have we learned already for our policy gradients lecture? So we want to take the grad theta of that expectation over actions of that reward function, okay. What I remember from our policy gradient lecture is actually we didn't know the rho. We didn't know, we said the reward function, we don't know it. And we came up with a formula for the gradient, if you remember. Well, that formula still holds now. Even the fact that we know the reward function, right, rho, still we can use our formula for the previous lecture. What is this formula, guys? Who would like to say something? Okay, so we have an expectation over actions. The actions are sampled from theta of S. The gradient with respect to theta, where in the case where we take a derivative of a distribution, where the parameters with respect to which we take the derivative parameterize the distribution. If you remember, this is exactly what we said. In that case, we open up the expectation. So we have this big integral and we multiply with p theta S. And so we have grad p theta multiplied with rho. And then we said the problem there is we don't know how to approximate this huge integral. So what we did is we multiplied and divided with p theta. Then we said that grad p theta divided by p theta is grad log p theta. So then what comes out at the end? What comes?
Expectation of grad log probability into reward.
Exactly.
We have to probably put rho instead of reward.
Say it one more time.
We'll probably have to use rho instead of reward because we don't have to.
No, because we are trying to maximize the rho. Forget about reward. So let's assume we care about this computational graph. All right? Is that clear, guys? And by the way, there are going to be questions in quiz 2 about here's the expectation, here is the derivative, what is the final result? You should be comfortable to say, okay, let me write the expectation as a big integral, a big summation, whatever you care, put the gradient, see if, actually I have a very nice summarizing slide at the end, so maybe I'll wait till then. So, but basically the thing is totally not surprising. So great. So now my question for you is the following. This likelihood ratio gradient estimator here, does it use the gradient of rho or not?
No.
It doesn't use it. I also don't see it anywhere there. Great. Now, however, this exists, right? Because we said we know it in this special case. Excellent. So now the good thing is that this essentially likelihood ratio estimator, you can use it wherever you know the gradient or not. Now, the truth is the following. Whenever you know the gradient, you need to be able to use it because gradients essentially tell you how much the function will go up if you change the parameters. This is super useful information as opposed to just sampling randomly and checking, oh, let me sample from actions. What the rewards did I get? Which is essentially what this estimator is doing. Okay, so let's see. Okay, great. So basically, in the special case now, where our policy is Gaussian, and to be completely honest, we haven't seen any other case. This shows up in all the papers whenever they have stochastic. Oh, we're going to use Gaussian. Okay. I'm pretty sure in 1-2 years the default will be very different. But right now many people use Gaussian distributions. So now you know what to do. So you go here, grad theta log, where p theta is now the Gaussian. Essentially, something like alpha minus mu is going to show up here, grad mu with respect to theta. And if you remember, that precise expression is what we showed also in our policy gradient lecture. Do you remember? And then we also showed how this gradient is going to look like if our p theta is a softmax. Let's say it's parameterized a discrete probability distribution. Do you remember? So there is no here any mystery of what is this grad theta log p theta, because that's precisely this thing here. Is that clear so far? Are we so far cool? Okay. Yeah. And now to be honest, I made this assumption I made that our policy only parameterizes the mu and the, covariance is fixed. All right. You just put it, you can make it also diagonal, you put sigma everywhere, and that's how this looks like this. Now, if you want to parameterize also the covariance matrix, it's going to be a little bit more complicated, but you can still do the chain rule and figure it out because you know the Gaussian formula, so you just take the derivative of that. Okay. Now let's see. So the alphas are sampled from a Gaussian distribution. Now, is exactly what I told you. Either you'll assume sigma fixed and is not learned, or you need to say, okay, I'll also learn the sigma, but let's assume for simplicity that I have one variance for all my action coordinates. Or you say, no, I want a different sigma I for every coordinate, and I want my network to spit out mu for each action coordinate. Let's say I have 2, steering angle and how much to press the gas. Let's say I have 2 for mu, 2 for sigma. Or you know what? I want to have a full covariance matrix and, 2 by 2 in this case, and I want to parameterize all the, upper diagonal. So essentially also the correlation between the 2 action coordinates. So all of those cases, all of those choices are totally cool for you to take. Many people take the first option, which is the simplest, but we'll see later. Many people also take the second. So just wait and we'll see when we go to model-based RL that, other type of parameterizations exist. So all of those fall under the umbrella of Gaussian policies. Now, we need to make so let's assume that we are in this case of sigma s comma theta. We need to make a tiny little digression to be able to understand the reparameterization trick. We need to go and understand how we can sample from Gaussian distributions. And this is actually extremely simple. And it's in this slide. Does anybody know or remember from Intro to ML or some statistics course how we sample from a Gaussian distributions? If I give you a sampler from a uniform distribution, do you remember? Approximately. Does anybody remember how we sample from a Gaussian distribution? If I have a sampler from a uniform distribution, what is the uniform distribution? Goes between, is essentially uniform probability for all your items in your domain. Uniform between 0 and 1, yes.
So you get your uniform from 0 to 1.
Exactly, the domain is 0 to 1 of that uniform distribution, yes. And you sample from it, let's say.
Yeah.
Okay, great. Let's assume it's this dot over there. You see the red thing? The red, let me see this guy. Yes. So let's say you have this domain, right? And you sample the hop. It shows up and you see all of them have equal probability and you sample, you got this guy. Okay. And then?
So you have a number between 0 and 1.
Yeah.
And then you pretend that that's the area under the Gaussian distribution. And then you find the like X that would correspond to that. Being
So,
the area. So you need to use the inverse cumulative distribution.
exactly. So your colleague said, I'm going to sample from this uniform distribution. I'll get a number, let's say 0.7. And then I'll say, what is the item X whose probability, what is the probability that things that I'm going to sample from a Gaussian distribution are going to be smaller or equal to 0.7? And to answer this question, you need to compute this cumulative density function, CDF, of your Gaussian density, which essentially tells you for every point on that x-axis, what is the probability of the samples having smaller or equal to this. So the CDF tells you for every item here, all right? So what is the cumulative probability of the sample that you sample from the Gaussian to be equals to this probability? And this CDF goes from 0, okay? So if you sample somewhere here, then this probability becomes 0. And if you go all the way to the other side of this x-axis, essentially is 1, because anything you sample will be smaller or equals to 1, right? Because essentially you sum all this area here under the curve, and this is equals to 1 because it's a probability distribution. Okay. Now this CDF goes from X to probabilities, but now you need to invert it. So you'll go from probabilities to X. So this, because you took this uniform distribution, this special domain between 0 and 1, the sample from that uniform distribution can be interpreted as a probability, okay, as a cumulative probability. And you say, okay, this is what I sampled, 0.7. What is the X here on the domain of my Gaussian distribution, which to the left of it, the area the cumulative area is equals to 0.7, and you say this is it, all right? Slightly to the right of mean mu, okay? Is that clear? Yes.
Can we know this in closed form, the PDF of non-zero one? So getting we can invert it in closed. I know that you can evaluate the CDF function, but I don't remember.
I mean, you just need to integrate, and you know the integral, the formula, right? Of Gaussian. So you just take integral from 0 to whatever of the Gaussian, okay? So now you know how to compute samples from the distribution, from Gaussian distribution, the zero mean and unit variance. If you know how to compute samples from the Gaussian distribution at the zero mean and unit variance, how can you compute samples from Gaussian distributions that have a general mean and any covariance matrix that I'll give you? This is what we'll say in the next lecture. Any question here, guys? Anything that you like us to repeat? Okay, so if you know how to sample from this Gaussian distribution of zero mean and unit variance, then you can form also samples from a different Gaussian distribution that has mean mu and variance sigma square. And how do you do that? Well, you will add mu and multiply with sigma. And indeed, can you verify that these samples have the right mean and the right variance? Yes, if you take the expectation, this will be equals to 0, and the expectation is indeed equals to mu. And if you compute the variance of this, it's going to be exactly sigma square. Okay? Now, what if you want to parameterize? So this was for unit variant Gaussian. What if you have a two-variant Gaussian? Okay? It's exactly the same thing. You can form it with the mu vector. This mu now is not one number, is a vector, plus L, where L, to compute L, essentially you need to form the Cholesky decomposition of the covariance matrix. All right? So in any case, when you know how to sample from the Gaussian, you know how to sample from related Gaussian distributions with a desired mu vector and a desired covariance matrix. That's the point here of this slide. So here is how the actions samples. Now, the action vectors that are sampled, that's how they are related to the z samples, where z's come from this very special multivariate distribution that has mean the zero vector and covariance the identity. Okay? Does this make sense? And do you see which we used? Let me go back to show you the red. We decided to use this parameterization. We said, you know what? I'll use some standard deviation. It's just I'll use the same standard deviation for all the action coordinates. So that's why I land here, there. All right. So, yes, so we said if you take now the expectation with respect to z is instead indeed mu, and if you take the variance is indeed sigma square and the identity. Now, here is the interesting thing. The expectation with respect to the actions alpha, you can rename them as expectation with respect to the sample vectors z. You see, and instead of putting alpha there, we can have alpha z, and I'll tell you why this is useful. But my questions for you are as follows. Does the sample's actions depend on theta? Yes or no? Yes. Do you agree? Okay. So do samples z depend on theta? Yes or no? Who says yes? Who says that the z vectors depend on theta, the parameters of your policy network? Okay, they don't. Look here. They're sampled from that constant distribution. All right? And the cool thing is that these actions have this simple form over those random vectors. It's super simple form. And the thing is that you can take the derivative of that form. And now we'll see how to do that. Actually, who wants to tell us what is this d alpha d theta? Is a very simple here. Yes?
It's like it's d theta
Yeah.
plus z sigma
D sigma d theta. Exactly. That's it. So d alpha d theta is now d mu d theta plus d sigma d theta. Okay? And who's going to give me the d mu d theta and d sigma d theta, by the way? Who's going to give me these derivatives?
I think the mu is like if it was non-Gaussian, if that's like the old derivative, that's like the action.
Who is going to give me this derivative, these analytical forms of the derivatives? Imagine that I have a neural network, right? This theta is a lot of parameters. How I'm going to get the d mu d theta and d sigma d theta? Yes? Yeah, and what is that neural network exactly? How we call that network? Based on what?
Like based on data.
How we call, guys, the network that takes as input the state and spits out a nu and the sigma and is parameterized by parameters theta. How do we call it? How? Yeah, that's a policy network. That's a policy network. The policy network parameterizes the Gaussian distribution. And what are the parameters of the Gaussian distribution? The mean and the variances. And here they are, okay? And then, so PyTorch essentially can give you this for free, all right? Because that's the output of your network. Is that clear? Okay, so I think here a small point of confusion is that our policy network sometimes is deterministic and takes as input the state and spits out directly action values, and sometimes it's stochastic and it parameterizes distribution, categorical distribution, directly the probabilities of different discrete actions, or continuous distribution, here the Gaussian. But we need to, just be comfortable with this. This is what it is. And we should be able to use it to take derivatives whenever we can in the right way, all right? Okay, great. So now that you know how to take d alpha d theta, then what is the opportunity that we get? The opportunity that we get is to apply chain rule. You know how to backpropagate through Gaussian sampling now. Well, before you didn't, okay? And you're going to see in that chain rule, we're going to use the d rho d alpha. Let's see. So here is what it is. Grad with respect to theta of the rewards, d rho d alpha d theta. All right. And d rho d alpha we know because we said that rho is an analytic function. You know what? I know it. That's what we said. And before it was the Q estimate at least. And this is the alpha d theta. And we have it right here on the slide. And now we can form gradients, all right, with the chain rule. So let's put side by side the two gradient estimators, okay? Two ways of computing parameters theta trying to maximize rewards. One is using the derivative of rho, and the other doesn't use the derivative of rho. Which one would you use? Which one would you prefer? Yes. Yeah. It has much less variance, that derivative of rho. Have you ever seen we to have a differentiable network and not to do gradient descent? Not really. Yeah. Yes.
If like we were not just having like one sigma value, we have that whole like matrix, then like you just change that like previous equation to instead of having d sigma, have like d like for like the whole like matrix, and it just be the same process.
Exactly. Yeah. You just apply the chain rule. Yes. You go back to your. You go back to this guy here, and then you say grad theta is grad mu plus grad of this L, and that's it. You just follow this chain rule, and the little values of the L and L, okay, are coming out of your what? Neural network. Is that clear? Okay. Exactly the same thing. Okay, great. So, yeah. So the pathwise derivative use the derivative of the reward with respect to the action. Great. So now let's go back to deep deterministic policy gradients. dq, d alpha, d theta. Okay, this wasn't the case that our policy was deterministic. So who would like now to tell us how would we adapt that if our policy is actually not deterministic, but Gaussian? Okay, how would we do it? So this is the policy deterministic, but hop, I changed it. I just put the actions to be samples. All right, so that's the first thing. You need to change the graph from square to become a circle. And just to be clear, this is how it's going to look like. Now your policy network will take essentially that z, all right, that is constant vectors, essentially random vectors, and going to be spitting out alphas in this way, mu plus z sigma. The mu and sigma would come out of your policy network, which is the theta mu, all right? That's what's exactly the output of your network. And those samples will enter into the queue. And my questions for you is, how we're going to form here the chain rule? Is this clear so far? It is totally great to ask a lot of questions here, guys, because we ask questions on these formulas in the quiz too. Okay. Yes.
I mean, we know it's dqda and d theta where theta are parameters, and we already calculated d theta, we already calculated d theta, so just plug it in.
We just plug it in.
D theta plus z d sigma d theta.
Yeah. Okay. And still there's samples. So still is an estimator, but those samples have much lower variance. So let's look at it. dq d theta, your colleague said, we'll form the chain rule dq d alpha d theta. And instead of putting here the deterministic network, he said, we already know how to take d alpha d theta. Like that. Okay. So basically we'll be sampling z's, we'll fit them in the formula and aggregate. Okay, that's what this means. The expectation. And we aggregate and we form a gradient estimate. And then we take theta nu equals theta O plus alpha, this gradient that we just estimated. And now we have a new policy, let's say network, correct? Is that clear? The paper that is not potentially super clearly written is called Learning Continuous Control by Stochastic Value Gradients. You see continuous control, so he's still wearing continuous action domain, but with stochastic policies, basically, yes, not instead of deterministic. So now, so how does this look like? Still, I see here, so the temporal difference learning, I learned some Q, so it's still a regression function, and then I take derivative with respect to that Q to estimate my policy, and then I iterate, collecting data under my policy, and then updating my policy and updating my Q. And the cool thing here is the policy is stochastic, and you don't need the epsilon greedy. You just need to make sure your policy doesn't collapse. And because it's stochastic, you can sample and it's going to explore for free. All right. Okay. Now here is a summarizing slide about computing gradients of expectations. This is the first case where we said that here is an expectation with respect to x, and we take a derivative of that expectation with respect to theta, but theta does not parameterize the probability distribution of the expectation, which is what the probability distribution, P of x. So P of x does not depend on theta, all right? So in that case, you just push the derivative inside and you're done. You're done, okay? And then you apply the chain rule, like whatever you want to compute there. Now, here is the second case where you take a derivative with respect to theta, but that theta parameterizes that px, which is the probability distribution of the expectation. In this case, we said that you can form the likelihood ratio gradient estimator, all right? Expectation. Okay.
But that would have high variance.
But that,
You can do this, but it's not a good option to do the basics.
right? And the alternative we just discussed is you can, for the specific case of Gaussian distributions. So, all right, so the truth is that there are similar reparameterization tricks for softmax distributions. I mean, they're not super, popular, I suppose, yet, but for Gaussian distributions specifically, you can do this reparameterization trick and take df dx, and the dx is essentially sample from the Gaussian, and dx d theta is essentially d mu d theta plus z d sigma d theta. All right? Yes.
So I know you said that like most people use like the Gaussian like distribution now, and you said like the convention might be different. Do you mean like there'll be like some redistribution that is parameterized with like different things?
Yeah, you can do similar reparameterization tricks for some like distribution, which we may or may not, we may see that actually when we talked about model-based reinforcement learning, and we may have discrete latent variables, and we may want to backpropagate through discrete latent variables, in a method called Dreamer V2. So we may be able to see the details of that. Yes.
I have just one clarifying question. With DDPG, we learned how to connect actor and policy together and maximize the Q function. And in the next paper, we learned how to make it stochastic using the reparameterization trick.
Yes. So the summary is as follows. With DDPG, we learned how to apply the chain rule through Q for deterministic policies. With the second part of the lecture, we learned how to apply the chain rule even when we don't have deterministic policies, but we have Gaussian policies. In both cases, we backpropagate through the Q function. Okay? All right, great. So we have 30 minutes. Any questions? All right. So there are two things that people care about a lot in reinforcement learning. The first is sample efficiency, how fast my algorithm learns, okay, with as little interaction with the environment as possible, right? We call this sample efficiency of the method. Now, the second is robustness, how robust my method is to the change of hyperparameters. A very obvious hyperparameter is the interleaving between collecting experience and how many gradient steps I take, and so on and so forth. So RL methods are notoriously sensitive to hyperparameters selection. So what we'll discuss next, maximum entropy RL, is some recent method, like maybe, let's say 2-3 years ago, like more recent DDPG, which shows much more robustness to hyperparameters. Okay, and it's a very interesting change. Now I'll tell you exactly what the change. This is the RL objective that we put down so far. Okay, and the truth is that in general, the maximizing policy of that objective can be totally a deterministic policy. Okay, and the truth is that stochastic policies are usually preferable. Why? I mean, in the general high level, let's say, way of thinking is that a stochastic policy should be able to learn multiple ways of accomplishing a task. Okay, I can reach to the mic in this direction, or I can reach to the mic in this other direction. All right, and there are better policies to fine tune from specific environments. If you know all the ways you can reach to a particular goal, then an obstacle shows up. Still, you are able to fine tune that policy, and the subset of ways that are stay alive, you should be able to discover them fast. While if you know only one way to reach to the mic and there is an obstacle, there's no way you can recover. You need to learn from scratch again. All right? They can explore better, and they are composable, which means if you have multiple functions and different functions have different objectives, potentially you can sum them up and have a policy that pursues the essential intersection of those objectives. Okay? I mean, this is in the ideal case where really you are able to solve the task in all possible ways. So imagine my one constraint knows all possible ways of being satisfied. I know all possible ways of satisfying the second constraint. Now I can take, the sum of these tuples or the composition of them, and I know the subset of ways that are holding both for constraint 1 and constraint 2. If I have learned only one way of achieving constraint 1 and constraint 2, this intersection would be 0. Okay, so there's no ways I can compose things. Okay. And there are more robust two hyperparameters. To do that, we need an objective that promotes stochasticity. Do you see? Does anybody want to say something? Have we seen anything so far about that in the course? Yes? Great. Yes, exactly. So we'll see how this relates to what we're doing in this maximum entropy, what we're going to call maximum entropy RL objective. So here is how this maximum RL objective looks like. I have my standard sum of rewards, okay, that clearly I want to maximize. And, so here I put some finite horizon capital T. If that capital T is infinity, then you need to put a gamma, a discounting factor gamma in front of the rewards, okay? And now there's a new term, which is the entropy of the policy, all right? And there is a scalar value alpha, which weights the maximization of rewards to the entropy. The entropy and the sum of rewards, the two objectives, all right? And the truth is that, the first methods that came out were very sensitive to that alpha, but then there's later papers that tell you how to tune that alpha automatically through training, all right? Now, just to remind you, what is the entropy of a distribution, of a random variable that follows a particular distribution? Is the expectation under event sample from that distribution of minus log px. And minus log px is essentially the information of a particular event x that has probability px, okay? So what does it essentially mean? What is the information? Well, the higher the probability of the event, is the information higher or lower? The higher px, the minus log px is higher or lower?
From one thing, then entropy will be 0. If it is equally distributed, that's an entropy.
Right, but now we're not talking about the entropy. The information is this minus log px of that event px. And correctly, you said that the more, let's say, probable is an event, the less I learn from its occurrence. And the more improbable is an event, the smaller the p, the higher the information. That's the definition, okay? And if that log has base 2, then this is essentially precisely coincides with how many bits I need to send to, let's say, my receiver, the fact that, oh, this event actually occurred, and this is essentially minus log px. This is the optimal way to compute your code and so on. This is from Shannon, okay? Now, if this is the information, minus log px, then the entropy of a random variable is clearly the expectation of this information. All right, this is called Shannon entropy, where the events are sampled from that distribution, right? The random variable takes values from based on the probability of this distribution, and this is on expectation how many bits you need to communicate that that value that actually occurred. Is that clear? All right. So that's it. So we want somehow the action distributions in every state to have high entropy. We don't want our policy to overcommit. That's what we're saying here. And we can compute the Qs of these policies, right? The same way we had the Q for our RL objective, we can compute the Q for our maximum entropy RL objective, exactly the same way that I'm going to show you how. And we're going to call this Q Q soft instead to differentiate it from the previous Q that only, took into account the sum of rewards. Are you all happy so far? Any questions? I mean, we did a big step here. We added the whole new term in our objective. So the principle of maximum entropy is essentially that policies that generate similar rewards should be equally probable. I don't want to commit to one over the other. This is exactly what we said earlier. I want to know all possible ways of accomplishing a task. And here is what your colleague said. He said, we did that before. I remember along with my policy gradient, I also had the gradient of the entropy, okay? And this is the entropy regularized policy gradient, essentially. You sum the two terms together, right? Is this equivalent to our complete objective? Not really. Let me tell you the difference. Adding an entropy gradient term maximizes the entropy of the policy in the present time step, okay? It doesn't tell you that I want you to find policies that maximize rewards, that lands on states that have maximum rewards and maximum entropy. Do you see? It doesn't take into account the future. Is that clear? So the maximum entropy reinforcement learning objective we put down 6 policies that lead to future states where the policy would have high entropy. It doesn't say, oh, in that particular state, just make sure the entropy does not collapse. Okay? Do you see that or no? All right, let's go through the analysis and we'll see. Now it's a good time here to talk about this Boltzmann exploration. You had also seen it, I think, in homework 1. So if we have discrete actions, and then I compute some Q based on my sum of reward objective, the standard objective, then what I can do to compute probabilities of actions is essentially exponentiate these Qs and compute in this way the analogous probabilities, okay, that are proportional to the exponent of Q. And this T that you see divided with the Q values is called the temperature of the distribution. And why it's called the temperature? Because as we hit the distribution, as we increase the temperature, the distribution goes closer to uniform. So no matter what your logits are, which is the Q values, becomes more uniform. As the T goes to 0, which means we're cooling off the distribution, this means that the softmax becomes very, very pointed. So the highest Q takes over and all the probabilities of other actions go down. Do you see? So you can make, starting from your Qs, you have, let's say, 10 actions, you have corresponding Qs, you can make more uniform or more pointed distributions by controlling the temperature of that softmax. But again, this is not maximum entropy reinforcement learning. Again, this greedily maximizes the entropy for the current time step, not for future time steps. It's just, it is, you know, much like the gradient entropy term that we saw earlier. Now, energy-based policies instead will take the exponent of not of the Q, but of the Q soft, where the Q soft has been computed while taking into account that entropy. All right? So Qs we know that are expected sum of rewards. Now these Qs are going to be expected sum of rewards and entropies on the Polish distribution of the future states. Does this make sense? So before we were seeking for policies that would land on states with higher rewards. Now we're seeking policies that land on states not only that give high rewards, but also have high entropy. Okay. Yeah, so compare this with the Boltzmann, which essentially is an exponentiation of the Q as opposed to the Q soft. Does this make sense? All right, now you may say, okay, we need to compute the Q soft. Yes, I understand that. So that's what exactly we're going to do. So here, for example, you can see how the ant, if you learn only one way to go to the goal X, once an obstacle shows up, then it fails. While if you have multiple ways to reach to that goal X, even if an obstacle shows up, the other way should be open. This is just a visual depiction of essentially this. Okay, so yes, so let's see. Let's go to backup diagrams that we know, which we use to compute those Q updates. Now we use them to compute the Q soft updates. Do you remember the Bellman backup diagrams? And because we care about the Qs, we're going to start from the dark black circle, go through white and then black. Okay, so if you remember, we said that the Q of pi, essentially the task here is you give me a policy and I need to return to you the state action value function of that policy. All right. All right, so we said that the Q pi of S comma alpha is the immediate reward plus gamma and the summation over all possible states that the environment sends you with the probability of that states under the transition function of the environment and the summation over all possible actions weighted by the probability that the policy puts on those and QP S comma alpha. Correct? You remember that we're taking the summation of all the values of the lifts, each one weighted with the probability of that lift. And the probability of that lift is a multiplication of, the environment transition and the action probability assigned from your policy. Do you remember that one? Okay, now the only thing we're going to do now is we're going to add an extra term, all right? Minus alpha log P alpha prime given S prime. This is essentially the information of actual N prime conditional state S prime minus log, okay? That's exactly the definition of the information. And that's it. It just shows up there as an extra term for the next state. Do you see? All right. So now I have this way, and there are two ways I can do it. Listen, either you're going to add the term on the state level, S prime on the white circle, or we're going to go inside the expectation and add it on each of the next black circles. It's exactly the same. It's exactly equivalent. In both cases, is an expectation of minus alpha log P alpha. Do you see that, guys, or no? Okay, so this is just a summation. Now you see that we have one white circle for all the black circles. So you decide either you're going to add the entropy of the next state when the next state rolls up, and that's totally great and super interpretable. This is exactly the entropy of the probability distribution condition on S prime. This is exactly this HP given S prime. To do that, you need to do a recursion that involves both Q and V, because you need to be talking about the state level, let's say. Now, if you want to make a recursion only with Q, then, which means that you need to go all the way down to the black nodes, then you need to have this alpha log P alpha inside the expectation of actions. This is exactly the same thing. Essentially, you open the expectation of that entropy, and then you aggregate the terms. That's all. So how can we do then soft policy evaluation? Let's go and see. So our Bellman equation was that. So now let's see the soft Bellman equation. Let's call it Q soft. The only change is we added this minus log P alpha prime given S prime. That's all we did. So this is the Bellman back update operator, and the soft one is exactly the equivalent. Do you agree? And how do we know that this converges? Well, we know that this converges because I can do this rewrite, which is very simple. Essentially, I take out and put again the entropy and where expectation over S prime sample from the transitions of your environment. And now you can group the immediate reward plus gamma alpha in the entropy term in that new reward called R soft. And now this operator looks much like the previous operator. And we know the previous one was a contraction. And now this one is also a contraction. And you know what? It converges. Okay. That's great. So now we know, okay, under this maximum entropy RL objective, if you give me a policy to estimate this Q value, do you agree? Which is good. This is called policy evaluation. Now, to be able now to update our policy, we need to do policy iteration. I need to update in my policy now to based on my Q soft estimates. Is that clear? Do you have any questions so far? Yes.
So is it because we have that Bellman operator, so now the entropy we're considering is not about current that it's it includes the future because we're doing the recursive
Exactly. Yes. The Q, very nice. So your colleague says the Q pi of S prime A prime, it takes into account both the entropies and sum of rewards of that future onwards. Exactly. Right? We put those entropy in the recursions. Great question. Other question? Yes?
Yeah, so the reason that it's more robust to other hyperparameters because it avoids that mode clash, right? That's the intuition. That's
yes. So, well, we haven't motivated yet why it's more robust. To motivate that, we need to go all the way to the function approximation. Now we're still discussing tabular methods pretty much. But the idea is that if you know multiple ways of achieving the task instead of overcommitting, during training also you are more robust because you don't overcommit, and then in the a light of new data, you need to completely shift your policy around. Okay. But yes, we'll get to that one. Okay. All right. So this is good. Now we know how to do policy evaluation, and now we need to go all the way to do policy iteration. So here is the policy iteration. Let me remind you how was the policy iteration for deterministic policies in tabular methods. First, we did policy evaluation. We compute the Q, and we said this converts to Q pi. And then we did policy gridification, if you remember, improvement via gridification. We would find states where the Q was, there was some action that offered advantage, which means what? The Q of S comma alpha was higher than the V of S. That's it. And then we switch. That's all. And then we showed that if you do that, actually you land in a better policy, which means what? The values of all states are higher than the values of the previous policy. All right? Now, how we're going to do exactly the same thing, but for the maximum entropy objective. And we'll call this the soft policy iteration, the soft policy iteration. So first, we're going to iterate between, of course, policy evaluation and policy improvement. And the policy evaluation is exactly what we discussed, and this would converge to Q pi. And then the policy improvement is essentially we'll find a policy that by minimizing the KL of that new policy to that exponentiated of Q of the pi soft of the old policy. All right? Okay. So essentially, we want a policy that assigns probabilities to actions proportional to the exponential of the Q state action values. Is that clear? And you can show that, and this is in the next 2 slides, that actually the same way that you can prove that, policy iteration lands in a better policy, okay? And the Qs of all states are higher than all previous states. The same way the Q soft of the new policy is actually higher than the Q soft of the previous policy. In the same way, you can actually show it here. Yeah. So I wrote down the math for you guys, but yeah, I'm not sure we should go now. You do exactly what we did for the policy iteration for deterministic policies. You iteratively open the expectation on the right-hand side here, as you see, till you are able to connect the Q pi old of STA to the P nu. Okay. So that's it. And this leads to a sequence of policies with monotonic release soft values. Now, to be able to make those things practical, we need to consider function approximation. Okay, we cannot just stay in the tabular methods. So we need to start parameterizing our Qs and policies with, let's say, phi and theta neural networks, and see how this essentially projection of that exponentiate of Q values can, work with some general policies. We are going to consider policies that are parameterized by random variables, but people do exactly the same thing with Gaussian policies. So how is this going to work? Well, much like we did so far for DQN and so on, and actor critic methods, we're going to have 2 networks, one parameterized, one Q for the critic and one for the policy. And the value function is still a regression. And the Q hat, the targets in this case, is exactly what we had. Immediate reward plus gamma, Q, okay, with bootstrap, minus alpha log of P theta of alpha. And what is precise is alpha t plus 1, st plus 1, is exactly the actions and states that shows up in your trajectories, guys. That's what it is. So we approximate the expectations with sampling. You sample trajectories, you feed their actual values there, and you compute the TT targets, and that's how you update the Q theta. Is that clear so far? And this Q is the Q soft, essentially. It's an approximation of your Q soft. Yes?
Going back to the KL slide.
Yes.
Does the Z represent just the sum of all the terms on the top?
Yes, so that it is a probability distribution. Exactly. Z is just the sum across all actions, exponent on the alpha Q pi all. Yes, that's exactly what it is. Yes.
So for our pi nu, if we're doing it for each like state, right? Are we doing it for each like ST?
Yes, for tabular methods, exactly.
And so like the thing on the right, that like gives you a distribution.
Yes.
Okay. So like, why not just like use that exact like distribution as our like pi nu, as opposed to like doing this like hard nu over tail divergence of like some like policy that we're trying to like some pi prime. Like if that's a distribution in itself, why not just like use that?
Yes. So let me tell you, for discrete actions, that's exactly what you're going to do. All right. So you'll take the softmax in exactly the same way. Now for continuous actions, things are a little bit more difficult. Now for tabular methods, it's all the time discrete actions. So essentially, this is the Boltzmann formula, exactly the Boltzmann formula, but instead of the Q being the Q is actually the Q soft. Do you see? So that's it. It's exactly the same thing. Now, so that's all. So for tabular methods, we know how to do. Is that clear? Essentially, I compute Q soft, and then I do the Boltzmann formula. Okay? Do you agree? Now the thing is, how we're going to do the projection becomes difficult when we have, let's say, continuous actions. Okay? Let's see. Let's see how we're going to do that. So the estimating of the critic is actually very easy, but the hard part is this projection, exactly what you just said. So let's see. So how we're going to do this gradient of this objective? Well, let's write down the KL. So it's an expectation under action sample from your policy, P phi, all right, of the log of the P phi of alpha divided by that exponent of Q distribution, all right? Now let's break this logarithm, the log of top and minus the log of the bottom. And okay. And this Z term is actually independent of phi. So you can just throw it away, all right? The normalization, the partition function. So we throw this away. And now the only thing I need to worry is these two terms, okay? Which is the gradient of that Q, okay, the log of the probability of the actions minus the Q. So let's put it back. And what are we going to do here, guys? We're going to use exactly the same reparameterization trick. So essentially, we'll assume that the actions are sampled from some Gaussian distribution, and our network parameterizes the mu and the covariance matrix. So then, when I take a derivative with respect to phi of that, I can form the chain rule, which means what? Grad with respect to alpha, grad of this with respect to alpha, and grad of the alpha with respect to phi. And grad of the alpha with respect to phi is exactly what we saw in our previous set of slides, grad of mu plus epsilon grad of sigma, and the epsilon vector is the same as what we saw Z. These are constant vectors. They don't depend on the parameters theta. You just sample from them, and that's how you find the gradient estimators. How do you feel about this? Exactly the same trick that we did before. Do you agree? Do you see this, the Gaussian sampling form here? Here, it's exactly the same thing. All right? And here, essentially, we do the chain rule. Grad of this with respect to phi, grad of this with respect to alpha, grad of alpha with respect to phi. All right. So
with our proposed algorithm, there are two interesting points I want to emphasize here. So when you look at the number of episodes.
So now I want to show you a small video to show the robustness of this soft actor-critic method on training on this specific and very, well-established benchmark of cheetah. All right, let's see. So this is the first author talking in the ICML presentation of that paper, okay?
With our proposed algorithm. There are two interesting points I want to emphasize here. So when you look at the number of episodes on the bottom left corner, that tells how many episodes we have consumed so far. And that number is very small. In fact, that is almost comparable to many model-based algorithms at the point when cheetah figures out how to run. Another point, typically deep reinforcement learning methods, they are very sensitive to random seeds. And therefore, researchers, they repeat these experiments with multiple seeds, and then they report the average performance, or then they pick the top 5 seeds or so and report that. So for this video, we also ran this experiment 10 times, but instead of picking the best seed, we picked the worst one. So this is the worst case scenario.
This is the worst case performance of the cheetah, all right? And you can see in many plots that shaded region around the orange curve is much thinner than with respect to other methods. And you can see there DDPG that we found today, which is pretty close to the bottom oftentimes. And then you see also PPO that we know. And then TD3, which is pretty much a double deep Q learning with some minimum, if you remember, that we took just to alleviate for maximization bias. So you know actually many of the algorithms that show up as baseline in these papers. Yes, and the last thing I want to say, which is very, very interesting, is the following. Now you have Q values, Q estimates. You can actually sum those Q estimates, and you can show that essentially you can take the sum of Qs and project it into a policy, and that policy actually will do will essentially will not be too much worse than actually learning the policy under the sum in the first place. Do you see what I mean? You learn the Qs independently, and then you sum them up and you project them into a policy and distill them into a policy. And the resulting policy, despite the fact it was never trained with a combination of the constraints incarnate on the different Qs, actually is going to do well. So I want to show you now this video that you see how the little robot is going to put, why it didn't work? Mm-hmm. So the first policy is trained to put the white cylinder across that vertical red line, the second along that horizontal line, and the combined policy, which is never trained jointly across more constraints, is able to put them in the combination of the two constraints, okay? So you just train the two policies and the third comes for free for you, okay? You don't need to recompute. So here you just see the trainings, how, as time progresses, that the robot is managed to put the Lego block there. And now you're going to see the composability. Yeah, so now it's the composability on the actual robot. Two policies. The first is trained to stack. The second is to avoid the specific green wall. And the new policy, which will not train for, will be to stack while avoiding the green wall, okay? Here is the combined policy, all right? On the rightmost video, we never trained for that environment to achieve that task. We got that policy simply by combining the estimate Q values of the first two. This is not possible to do if you don't have those maximum entropy reinforcement learning policies, okay? You'll get your Q, you'll sum them, and something crap is going to come out, all right? But while here, because exactly they're stochastic, you can learn all possible ways. You can actually find intersections and so on. And by the way, there is a lot of research on those energy-based models, exactly because of those composabilities. Egon Mortach has actually written many papers on that topic, and they're all wonderful, and you can go and check more. That's the end for today, and hope to see you on Wednesday. And the lecture is going to be much easier, and you should come on evolutionary search for reinforcement learning.